Oh, the end of the semester.
Did you ever make up a new homework?
No, I didn't have time. I'm not going to change anything except we're going to go up through 16.5. So this next test is going to be 15.6 to 16.5. I like that symmetry. And then after the test, we will talk a little bit about 16.6 and 16.7, but they probably won't end up being on the actual final. We'll just talk about it, and we'll see how much you pay attention to me talking about it. I desperately want to finish up. What's up?
Are we going to be doing that on Wednesday next week? That new stuff? When are we going to be doing reviews or finals?
Yeah, first thing on Wednesday. I'm going to talk very quickly about it. We'll see what happens. So this Wednesday, of course, I'm going to have the answer key for that practice test, but I think this Wednesday I'm going to try to make it more about looking at specific homework problems to get the process down. So this Wednesday I think I'll make it more of a... I'll give you the answer key to the practice test, that's great. But I want to kind of make it more where we focus on some homework type problems. Homework problems themselves, or just problems that are a lot like your homework. That might be something I would put on the test. Because there's something I want to get into very quickly here, very soon, which is a weird little process about partial integration, right? To figure out something. Let's jump into it. Any quick questions from homework? There's no such thing as quick questions from homework in 281, but we'll see what happens.
It's 1528. Problem 28. Oh no.
Which one? Sorry?
Yeah, it's problem 28 of 1528.
Oh yeah, so 28. Find the average. That's the one about the average distance, right?
Yeah.
From a point to its center. From a point in a ball of radius A to its center. So, I mean, how do you find, well, first off, what function am I going to be working with? Yeah, like the distance formula, right? For three-dimensional, I got a sphere. So I'm talking about some point in a ball of radius A to its center. We can say the center is at 0, 0, 0. Like we got a point at X, Y, Z. I like it. So, how do you find the average something? It's crazy. Yeah. Yeah. Well, so think about that. To find I'm trying to remember what they showed us in this section or earlier section. I think it was the earlier section where they talked about averaging functions over something. But, I mean, it doesn't matter what coordinate system you're using, you still do the same thing. You still find the average function value the same way. And that's all I want to do here. I want to find the average function value where the function is the distance formula. You would maybe think that, but that's not true. Yes, it would be. It would be closer to the edge of the sphere. Because in a way there's there's like more points out there in a way. Not really, but oh well, that's a good way to look at it. Freakiness. You're like, that didn't help at all. And, oh well, that's the way it goes. Has anybody tried that problem yet? Some of you have? Okay. Alright. Does that get you thinking in any direction of anything? I mean, look about how to find the average of a function. You got the function you're trying to find the average of. No, it's integral. I mean, so yes, an infinite sum, yeah.
Can you be more specific?
No, sorry. If that's the only one you're having trouble on, that's fine, because that one is a little bit freaky, but it's not as bad as it seems when you first read through it. Go back and look up how to find the average of a function. Try to extend back to 3 dimensions. I couldn't remember if they gave you an averaging. I'm pretty sure they do. An example of averaging over 3 dimensions?
Yeah.
Yeah, okay. All right, cool. So that one sounds extremely freaky, but it should not be too bad. You know the function you're dealing with, and you know how to find the average of any function over a region. So in 2 dimensions, you find the integral of the function, then you divide by the area over which it's operating. In 3 dimensions, you find the
volume, or the 4-dimensional space and divide by mass.
yeah. So in 1 dimension, how do you find the average? In 1 dimension, you integrate, and you divide by the length. So in 2 dimensions, you integrate and you divide by the area of the region. Oh, so it's, I don't know if I can take that one next step. Okay. Anything else that I can be very vague about? Yes. 32? Oh, one big thing there, when it says, where'd it go? Proportional to its distance from the center of the base. So what does that mean?
It's the same as the center of its distance from the origin.
So proportional, if you're proportional to something, if A is proportional to B, then A goes like K times B. Alright, that's one thing to realize. Where'd it go? Oh, and this is just, okay, this is just plugging and chugging, find the mass, center mass, the moment of inertia, and just taking you back to those equations for those things. I think they gave, yes? No. Yeah, they give it here, don't they? Oh yeah, they give it back earlier, don't they?
Yep.
Somewhere here. I can't remember. Oh, there it is. Yeah. Center mass, inertia, all that kind of stuff. Now, to be honest, like with the homework, obviously the homework covers more than the tests do, because otherwise the test would have to span a week to cover everything. Homework is all about exposing you to different things. So some of the applications of the processes we learn in mathematics, they might not show up on a test, because it all depends on where you go from here. Now, some of them might, hell yeah. And if it's something weird that I didn't really spend a lot of time on, I'm going to have to give you the setup, right? But when you're doing the homework, you just look up the setup. You see what it needs to figure out the mass. What do they ask you for here? Find the mass. Go back and see how do they figure out the mass from something. Figure out what you need to plug in there. I like it. So in that level, application problems are more about the form of what you need to do. It's really awesome if you understand why the form is the way it is. Right? But, I mean, at the level of homework, you go back, you figure out what you need to do this process, and you get what you need, you plug it in, and you do the process. Right? Let me see, did I actually help you out at all? A little bit? There are examples that show you, or not examples, but there's actually, they set up how to figure out the mass. They just want you to convert it to spherical coordinates now.
For the center of mass, like I understand, like if you're trying to find the center of mass of like x, y, that you, for rectangle, you put like the z into it, into the integral. Wouldn't you substitute since z equals whatever z equals in center, you would just convert that and put that inside?
That's the type of thing you want to do, yeah.
Right.
Yeah. You want to convert the process in rectangular, convert it over to spherical. attack it, lock it. So really this kind of problem is me trying to get you to realize what this stuff is used for in real life, and also to get exposure to a different way of looking at conversions. The more I can get you to convert things in these problems, the more the conversions will stick in your head a little bit. The more you'll remember what the hell phi is. Poor little phi dude. Alright. Okay, maybe. Anything else from homework that I can gloss over quickly? Pretend like I answered it. I mean, those two problems are... I mean, one of them was just plug and chug stuff, but the other one was a little bit freaky, but it's all based on stuff we've done before. We've figured out averages of functions before. All right. So see, where we leave off, I think we left off, we finished section 16.2. Believe it or not. And really, so when you do a line integral through some kind of a field, it's sort of an accumulation of the effects of that field along that path. Okay, that's one way of looking at it. I like it. So what we're getting into now, 16.3 is basically one step from 16.2. What's really important in section 16.3 are some of the terminology that they bring up. It's going to become huge in some of these later theorems. So the main thing about 16.3 is this idea. Oh, let me set this up. Let's say... What else we got? What's this here? Gradient. I love it. Cool. Today we're going to talk about this operator by itself. It actually exists on its own. Poor little dude. Oh, so if you got all this here, the integral over some curve is equal to, yeah, little f dude. Which f do I want? Do I want that f or the other f? Oh yeah. I missed one step here. I mean, what does this look like here? What does that look like? And it's funny, I like the fact that we use big ass F because it's the same big ass F from Math 180 in a way. It's not really, but we can look at it in that way. So F is differentiable. This big ass F is differentiable. I'm sorry. This little ass F is differentiable. The gradient of F is continuous. This is doing what basically to this function F? No, be careful. That's something else entirely. There's no dot here. This is not a dot product. This is kind of a weird little thing, to be honest, in terms of vector happenings. This is kind of a weird little dude, but...
Is that gradient little f or gradient big F? I think.
Gradient little f. Oh, here. Yeah. The gradient is basically doing what to little f? Basically differentiating. Right? So when I integrate the derivative, that sounds like the fundamental theorem of calculus. Right? I just have to evaluate it at the endpoints. That undoes that differentiation. So, I mean, there's a whole proof I'm not going to go through. But C has got to be a smooth, let me see if I can get all this, smooth curve. Which maybe kind of makes sense. You can't have anywhere where it does something freaky. All right. F has got to be differentiable. The gradient's got to be continuous. You got all these little things. There's all these weird little functions you can create and find counter examples, but they don't meet the requirements. So of course they're not going to work the same way. All right. Maybe. So what becomes important is, let me see if I want to do an example. No. Well, no, I don't like the example. Okay. Let's see if I can. Oh, okay. Perfect. I'm trying to figure out how to tie this into later. So I got some vector field that I'm integrating along a curve in that vector field, right? So remember that little blah, 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 blah. Now, something has to be true about this vector field in order for this to be true. Now think about this. How many ways, if I got a point A and a point B, and all I need is for C to be smooth, how many ways can I connect those two together? Because there's nothing else about C except it's just going to be smooth, right? So any path that I take, it doesn't matter which path I take because the integral along that curve, if there's something true about this field, the integral along that curve is going to be the same. No matter if I go this way, I call this curve 1, or if I go straight, I'll call it curve 2. Or I go around and I say, well, I'm going to take it from the other side. Wow! Well, that's curve 3. But notice there's something implicit in here that kind of makes sense. The only reason this really works is because this came from this. And that's not always true. I can't always find a little f that I can take the gradient of and get this big F. All right, that's the important thing right there. All right, maybe. So it's really weird the way it kind of ties into itself in multiple ways, this idea. So if there is such a thing as the gradient of some function equals the vector field I'm looking at, then this will be true. This is what we call path independent. Sure. I like it. It's really weird to introduce this topic because it kind of ties back into itself in so many different ways. So here's another interesting thing. 2 theorems in quick succession. I like it. Yes, cool. On page 1129, there's the theorem that says, suppose F is a vector field. Page 1129. Theorem number 4 says, say F is a vector field. Continuous on an open connected region. So we got a couple things to talk about. Open connected region D. So let's talk about that for a quick second. Open means that, well, the official definition is kind of weird, but it basically means that if I have some curve enclosing some region, D is the interior of this. It does not include the actual curve around it. It does not include its boundary points. That's what open means. It's like an open interval. If I wrote this 1 to 7, do I include 1? Okay, good. So that would be an open set. It does not include its boundary points. All right, so these little words pop up in these theorems that you want to kind of double check and make sure you understand what they mean. Because if it wasn't open, there are things that could happen that would make the results untrue. So it's got to be open. So D is contained, but it doesn't include C. It's got to be connected, which means that I can connect at each 2 points and stay within D. So there can't be any holes in this poor little dude. Right? I think there's pictures showing you connected. Yeah.
So it's just the difference between connected and simply connected or something.
Page 1130. Yeah, simply connected. I'm thinking about simply connected. Open, connected, region D. Simply connected versus connected. Where'd you go, connected? Oh, okay. Yeah, that's what I said, and then I drew the hole. So any 2 points in D can be connected by a path that stays in D. The simply connected would add the extra thing where it can't have any holes in it. I like it. So connected, and basically you can't have any D that's like separate from it. You can't. So if D was this, that ain't gonna work because it can't start from there and go there and stay in D. I have to kind of hop outside of D. Okay, I like it. I like it. So I mean, one thing you guys want to do is to really kind of get to know what these words mean in these theorems. Just going to get a feel for what they mean and why they're called what they're called. Connected kind of makes sense. You should be able to connect any 2 points and stay inside that region. Blah, blah, blah. Here we go. All right. Continuing this. If this is independent of path, then F is conservative. And there exists, well, this is in the book, I don't know why, that's why I put this here. So if you're writing this down, I don't understand. And there exists a little F such that delta F equals F. Delta little f equals big ass F. That was the big thing from this guy. In order for this to be true, in order for it to be path independent, there has to be a little f dude such that the gradient of it gives me the big ass F.
Delta F or gradient F?
Well, again, the symbol is called delta. I always read this as grad F, to be honest, but I have heard it as del F, because the curl will be del cross F and the version will be del dot F. But I always just call this grad F to make sure what the hell I'm talking about. All right. Where'd I go? There we go. Blah, blah, blah. So if you're, so this idea of a conservative field is one where, and this ties in beautifully with this picture. If I go around a closed loop inside of a field, and all along the loop, if I'm pushing against the current this way, then I'll be going with the current that way. So one of the most easily imagined conservative vector fields would be something like this. Any closed loop I create in that field, if I go around it and integrate around it, I'm going to get 0 at the end. Yeah, I like it. And why does it make sense from what we were talking about here? If this is path independent, if C1 and C2 and C3, they all give me the same integral. They all give me the same value when I integrate along it. Is everybody cool with me so far? That's what I was saying earlier, right? So I get the same value for the integral there, the same value for the integral there. So what am I going to get if I go there and then go backwards? I'm going to get integral value and negative integral value. So the whole thing is going to be 0. That's going to be true for any closed loop. And you can see it from here, of course. If B equals A, then this shit is 0. Right? You guys kind of with me now? Again, what lets that happen is that there exists an F that when the gradient is taken of it, I get big ass F. So it goes both ways. It's one of these if and only if situations. This vector field is conservative if and only if the integral is equal to 0. This is, I can evaluate this at the endpoints if and only if f is conservative. They all kind of go together. So it really becomes a situation where, like, how the hell do I tell if something is conservative? And then how the hell do I find this dude? Okay. If you're semi with me, let's see. So since a field being conservative means that I can find the integral just by looking at the values at the endpoints. Shit, yes, please, dear God. I want to do that, thank you. Yes, of course I want to do that. And not mess with all this other crap and t's and dx. And I don't want to do all the crap, I just want to look at the endpoints. I can only do that if it's conservative, if I can find this little f. So how can I tell if it's conservative? And then once I know it's conservative, how do I find the little f dude? That's what we're going to focus on right now. I like it. That's a lot of colors for you, Jeff. All right. Oh yeah, good. Oh, okay. So here's how to tell if F is conservative. Step one, look at its voting record. No, step one. So this is oh, Jeff. Oh, shit, Jeff. I have to apologize. I'm sorry. So how to tell if F is conservative? Well, let's say that F equals, and this should sound familiar, P is some function of x and y, P dx, plus Q dy. We've looked at that before, I think, that form. And of course, I'm leaving off, get out of there, get out of there. Get ahead of myself. There we go. So F is as you go back to the very first handout that I gave from section 16.1, when we were filling in and trying to draw all the vector fields by hand, I had to give you something, and of course I gave it to you like this, but it's the same idea. Right? Those notations are the same. F is conservative if and only if, I like that, if and only if dp dy equals dq dx. It's very weird. Oh, let's see, don't want to, it's actually not that horrible.
It's like taking fxy and fy.
Exactly, yeah.
I love that.
But the P and Q are separate, separate functions. They could be functions of x and y. Let me see if I want to tell you. Oh yeah, all right. If this exists, and what is this? If I give you that F is, let's see, what do you want to say? All right. Say F is, like I already have, Pi plus Qj. If this exists, then what must be true about, so delta F equals F, right? So what does that mean? What's the components of grad F? What's the components of grad F? I keep saying delta, I know the symbol is delta. But
Would be partial F of x, partial F.
I like it. Cool. So if this exists, then that must mean that P is Fx and Q is Fy. And guess who we're going to use next? We're going to talk about Clairaut. Right? He's the guy that said the second partials are going to be the same. So if I take the second partial of, where am I at? I like it. Oh, good. All right. If I take the partial of this with respect to y, that's the partial. I'm not going to write it all out. That would be df dx, d squared f dx dy. And then this will be the other way around, but Clairaut says that those have to be equal if you have some nice function. And our whole theorem is talking about that function has to be differentiable. It's got to be nice.
So that's how you know the function is.
So that has to be true. Because that's basically the second derivative. That's the derivative with respect to x and then with respect to y. That's the derivative with respect to y and then with respect to x. Clairaut is the guy that said they have to be equal to each other. So it's a really interesting little path we took. If this exists, then this must be true, which means this must be true. So then we've got a test for a function. If that is true for a vector field, it must be conservative. It must come from the gradient of something. So if I know that if I take the gradient of something and make a field out of it, it's conservative right off the bat. If I know a field is conservative, that means there must exist a little function f that I can take the gradient of to get it. Ooh. And then I can use the fundamental theorem of line integrals, if you want to call it that, the F-Tolk. Yes?
So then, at that point, if you know it's conservative, then you just take, you just integrate P with respect to x and Q with respect to y.
Yeah, now you can just take, where am I at? Well, let's do an example. Maybe here's where we should do an example. Let me see if they give me a full one where we actually. Oh, let me see. Let's do this here. No. Well, all right. Let me build up to that. Because what you're thinking about, if I want to use if I'm given a vector field and I show that it's conservative, how do I use the theorem for line integrals, the fundamental theorem for line integral? How do I use it? I have to find f. I have to find little f. So let's focus on that for right now. So let me see. Here's a little example. Oh. There we go. Let's put the page number down there so I look it up. Let's try this one out real quick. If I am you, to make this a little bit easier to track, identify immediately what P and Q are. It would be remarkably evil if they switch these around, but you never know. I wouldn't do that to you on purpose, but I have to cover my ass there for a second. So, of course, what's P going to be? What's the function P?
Y squared e to the x.
Yeah. So Q is this other guy.